Hello class, welcome back. Today I'm going to be going over chapter 10, where chapter 10 is, chapter 10 goes over waves and sounds, right? So, waves and sounds, I think, are another one of those things we have, like, everyday, experience with them. So some of these things may be, a bit more intuitive, while some of the other concepts we talk about may not be. So here in this video, I'm just going to be going through the PowerPoint on Blackboard, basically going through vibrations and waves, wave motion, transverse waves, and longitudinal waves, sound waves, reflected and refracted sound, forced vibrations and resonance, interference, Doppler effect, sonic booms and bow waves, and musical sounds. All right, so let's get right into it. So first, we start with the, just a kind of general definition of a vibration and a wave. So a vibration, and unlike the definition that we use here on the PowerPoint, is just a wiggle in time. And vibrations cause waves, which is a wiggle in space and time, and it transports energy. Boom, boom. Okay, so a wiggle or vibration is basically just a wiggle in time. So we know basically everything is vibrating on the molecular level, right? Because molecules are always vibrating. And then those molecules that are vibrating are giving off waves, which are basically vibrations in space. Obviously a wave looks like this, whereas a vibration can just be, up and down, something that's shaking up and down. But this is like an up and a down, but going in space. So it's like going up and down, but I'm also moving to the right in space. So now let's kind of think of a physical example. If we think about a pendulum, well, not a pendulum, but something on a spring, right? I'm gonna do two examples. This box is on a spring, and I pull the box down, so now it's here. And then once I have the box here, what's gonna happen? Well, once I let it go, it's gonna go up, right? And then fall back down, go back up, fall back down, go back up, in a repeated motion. So that there is gonna be our vibration, basically. So now if I produce that vibration, so produce that vibration, it's going to go up and down, but I also move something underneath it, like a piece of paper to the right. So as I go up and down, try that again. Move up and down and move the paper to the right. Not perfect, but you kind of get the idea. It's going to make some type of wave like this. So it's going to look something like this. So this is basically the wave that's created by the vibration of this box here. All right, so now let's look at this wave here and define a few things. Boom. This here is just a standard wave. So now I'm just gonna label what a few things are on this wave. Well, for one, this wave has some speed, so it has some velocity because it's traveling in space, right? So it has some speed, v. It's traveling in that direction. This wave also has some wavelength, where the wavelength is going to be basically measured from here to here. So from this point to this point, that's what we call the wavelength. actually, excuse me, the wavelength is actually from here to here, from top to top, or from actually, no, I had it right the first time. That's not a wavelength. The wavelength is from here to here. Yeah, so once it completes one full cycle, that's one wavelength. Now, basically, this wave could continue on. So, like, it would continue on like so. So let me label this. So from here to here, that's a wavelength. But measuring from here to here is also the same as measuring like from the top of one point to the top of another one. So here to here is the same as here to here. So like this is one wavelength because that's how long it takes for it to do one full cycle. So, you know, you can imagine the spring, you know, this is when it goes up, it goes back down, and then it goes back to where it started. So once you go back to where you start, that's one full cycle, or one full period, we call it. So this from here to here is one wavelength, where if I started here, if I start at this point, I get back at the same point once I get over here. And so basically that would be, you know, another representation of the wavelength, if it's easier for you to see it that way. You know, it's basically the distance from the tops, or you can start from the beginning and just look at it from there. So that's what we call our wavelength. Now, we also have another thing we call the period. Let me go over the period. So the period is how long it takes for it to make one full cycle. So period. Oh, that sucks. The period is the time to make one cycle. When I say one cycle, I mean like the time it takes for it to go through one wavelength. So the time it takes for it to go from here to here, because this wave has some velocity, the time it takes to go from here to here is one period. And so for that one wavelength, it travels some amount of time. For the period, we usually use the capital T. So the time it takes to go from boom, there to there is one period. Okay, so now we also have another thing in waves that we call frequency, right? Where frequency is basically, you know, how frequent or how fast, you know, it's kind of, they say how fast it's oscillating is basically what frequency is. So like something like this, I can't see that. Something like this has a really, really high frequency because it's going, you know, up and down really, really fast, versus something like this probably has a much longer frequency because it's actually pulled outwards, or, you know, it takes more time for it to go through one wavelength. So like one wavelength would be like right here, or let's say from here to here, be one wavelength. So see that it's stretched out, so it takes basically more time for it to make that one wave pattern versus here. You know, the wavelength is really small, so the frequency is a little higher, way higher. So the frequency is actually given by, right over here, frequency, and we usually use a F to represent that. Frequency is equal to the period, but the reciprocal of the period, basically. So 1 over the period. So 1 over the period gives you the frequency. Boom. So that's key. 1 over the period gives you the frequency. So if you know the period, then you can find the frequency. So now let's say you know the period, so you can find the frequency. Let's say you also know the wavelength. And the symbol for the wavelength is given by a Greek letter called lambda. And wavelength, well, is measured in meters, right? Because it's an actual length of something. So wavelength is measured in meters, period is measured in time, right? Because it's time. Frequency is measured in hertz, something called hertz, which is basically, it has a unit of 1 over time, because time's on the bottom. So now if we combine the frequency with the wavelength, it actually gives us the velocity of the wave. So the velocity of the wave is going to be lambda, which is the wavelength, times the period. Not the period, but the frequency. Boom. So I'm going to be reiterating this equation more and more as I go through the lecture. Just to kind of give you a base idea here is this is our wave. You know, this wave has some wavelength and it also has some velocity. And so if we know the period or how long it takes for it to go through this one wavelength, then we could find the frequency. Then once we know the frequency and the wavelength, we could find the speed of this wave. Okay. Now, one other thing we have on here that I did not label is the amplitude, which is just how high up this way or how low down this way the wave goes. That's what we call the amplitude. Amplitude. Boom. All right, so now let me give you some physical examples of, you know, what these different things do. So I'm gonna write out a few waves here. Okay, so let's compare these two. So firstly, you see that this one on the top it's a lot higher. It has a higher amplitude. And this one has a low amplitude because it's really, really short. So this high amplitude, if this were like a sound wave, this high amplitude would be associated with. So high amplitude means it's going to be louder. So if you increase the amplitude, you basically increase the loudness of the sound. And for this one, notice that it kind of goes up and down really, really fast. So it has a high frequency. So we increase the frequency. That increases the pitch. So, you know, a person that has like a high pitch voice, basically their vocal cords are vibrating at a high frequency. So just to kind of give you like a physical example of, you know, what the amplitude kind of represents on this wave here and what the frequency would represent on this wave. All right, so let me just look through the slides here, make sure I didn't miss anything. Okay. So just to say a few more things about that. So vibration, which again is just a wiggle in time, right, is described with the frequency. But a wave, which is a wiggle in space and time, is described with frequency, speed, because it has some wave speed, and what else? Wavelength. I'll use lambda. So a wave is described by its frequency, its speed, and its wavelength. And we know the relationship between those is just v, which is the speed, equals frequency times wavelength. Okay, so for example, if I say, well, looking at example number 12 on the slides, it says we have a frequency of 20 hertz. All right, so then what is the period? How can you find the period just from knowing the frequency? Well, we know basically the frequency is equal to 1 over the period. So we can rewrite that as, well, the period equals 1 over the frequency. And so the period t here is equal to 1 over the frequency. Well, we know the frequency is 20. So the period is going to be 1 over 20. Boom. So from the frequency, you can find the period, and same vice versa. If we know the period t, if the period t, let's say 5 seconds, period t is 5 seconds, well, the frequency then would be, it'd be what would be 1 over 5. So it'd be 1 over 5 hertz. Boom. All right. So now let's say we know, going back to this example, the frequency is equal to 20. Let's say the wavelength is equal to 100. Then what would be the speed of this wave? What would v be, the speed of this wave? Well, we know the speed of the wave is given by the frequency times lambda, or the wavelength. So then we'll just multiply those two. So 20 times 100, 2000. So this would be the speed of the wave if it had a frequency of 20 and a wavelength of 100 meters. Okay, so I think I've kind of given you a good little basis of waves and vibrations, frequencies, periods, wavelengths, all that. So now let's talk about the two kind of waves there are. So there's two kinds of waves. There's there's transverse waves, and then there's longitudinal. How do you spell that? I-T-U-D-I-N-A-L. I think that's how you spell it. So there's the transverse waves and longitudinal waves. So in order to think about transverse waves, it's a little bit easier to think about a wave in a different way. So if you think about a wave as pressure fluctuations, so if you think it as pressure fluctuations, I don't think I spelled that right. So pressure fluctuations, or fluctuations of pressure. Basically what I'm saying here is, if you imagine, how, sound works when you talk to a person, well, what's happening is, one, your vocal cords are vibrating, and then once your vocal cords vibrate, they produce some wave in the air, right? So, say you got a person here, some person here, and he's talking. So his vocal cords here are vibrating. They're vibrating. It produces some sound out of his mouth, which produces some wave in the air. So we have some waves coming outwards like this. So, but these waves here are not moving like, water waves like that. These waves here are moving like this. So like, this is what I mean by pressure fluctuations. So he's basically, talking outwards, causing the air to fluctuate like this. And this is what we call a pressure fluctuation. Because as my hands get closer, the air pressure gets, tighter and tighter or greater. Then as my hands expand, the pressure decreases. So this is also kind of a wave motion, if you think about it, because it goes in and out versus a up and down kind of wave. So this in and out kind of wave is what I mean by a transverse wave. A longitudinal wave is one that goes up and down like so. So, I think a good way to remember that is, well, I think it's easier to just remember longitudinal. So this is longitudinal wave, excuse me, because it kind of goes like long ways. So left and right, it goes long ways. And this is a transverse wave. A transverse wave goes, actually, let me check. Yeah, so transverse waves. This one goes up and down. Longitudinal waves go, how can I draw this? Let's see. Kind of go in and out. I guess, see how do they draw it? Yeah, so I guess if these were slinkies, the longitudinal wave would be if you were to push a slinky in and out towards the left. And a transverse wave would be more like if you shake the slinky up and down like a jump rope. So a transverse wave would be an example of a jump rope, you shaking a slinky up and down, whereas a longitudinal wave is more like, sound waves that kind of emanate from your vocal cords into the air, or maybe something like a water wave, like a water wave in the ocean. It kind of goes in and out. The waves don't really go, they do go up and down, but if you kind of sit at a beach, the waves come up to the tide and then they recede and come back. Then the waves go up to the tide, then they recede and come back. So they're kind of going more so in and out. So let's see, question number 16 on the slides say the vibrations along a transverse wave move in a direction. So the vibrations for a transverse wave, so these arrows here represent the directions of the vibration, right? And so see, we're vibrating up and down, but the wave is going, this way, left and right. So basically the vibrations are perpendicular with the wave, whereas for a longitudinal kind of wave, the vibrations here are left and right, left and right like this, and then that's also the direction of the waves. So here, this part was kind of scrunched up. That would be where my hands are like pushed close to each other. This part, when they're more spread out, and then here they get more scrunched up. So it's kind of going in and out like that. Okay, so let's see. So now on the slides, we actually use sound as an example of a longitudinal wave. Because basically your voice is compressing and expanding as it emanates outwards. Then you can kind of imagine a person with a high-pitched voice. They have a person with a high-pitched voice. They speak at a higher frequency. Or you can imagine a person with a low voice. Then they must be speaking with a lower frequency. And that's just kind of determined on, you know, how you talk, your vocal cords, and all that. And of course, if the person is talking louder, like if he's screaming, then his, sound wave of his voice has a high amplitude if you're yelling. But if you're whispering, then your voice has a low amplitude. But notice that in air, all sounds travel at the same speed. So even if my voice has a higher frequency or if my voice has a higher amplitude, that doesn't affect how fast it moves in air. So like if I yell, that's not going to make my voice travel any faster than if you whisper. So the speed of sound, I call it VS, the speed of sound is roughly about 340 meters per second. So you can kind of imagine if you're standing over here and you say something, your voice is going to travel, boom, your voice is going to travel 340 meters in just 1 second. In 1 second. So the minute that you start to talk, or the second that you start to talk, your voice already traveled 340 meters. So that's pretty fast. So that's basically just how fast your voice travels throughout the air. And so if you were to speak louder, your voice would still travel at this same speed, but of course it would have some higher amplitude, right? So it'd be more like that. All right, so now let's see. So now on the slides, looks like they talk a little bit about sound. I guess I already talked about that a little bit. So since now we're talking about the speed of sound, and this is basically air. Air would be the medium that sound is traveling through. And we know basically sound can travel through other mediums as well, right? So you might have heard like people saying, if you're on a railroad track and you don't see, a train coming, so it says train over here. Here's the railroad track way over here, and here's you and your friend. Y'all are both walking on the track, along the track here, but you can't see this train that's way far away. So you can't see it, nor can you hear it. But the train, since it's rolling on the track here, is causing the track to vibrate. So if you were to put your head to the track, you can actually hear or feel the vibrations of the train much faster if you were to hear it throughout the air. So if I were to draw it out, it would look something like that versus here in the steel. it's going to travel a lot faster. So all that just to say is the speed of sound changes for the different mediums that you're in. So for the speed of sound in steel, it's going to be equal to basically 15 times 340. So it's 15 times more. And sound also travels faster in water. Speed of sound in water is about 4 times as much. So we see that when sound travels through different mediums, it basically affects how fast the sound travels. All right, so sound in regular air is just 340, while sound traveling in steel or in metal is about 15 times faster, and sound traveling in water is about 4 times faster. And so now, the speed of sound can travel based off the mediums it's in. Well, what about the temperature? Because you can have different temperature mediums, right? You know, so it can be really, really hot in one area and really, really cold in another area. So since we know sound is traveling through air and the speed of sound is dependent on the medium it's in, if air is at a different temperature, that's almost the same as basically changing the medium that the air is traveling in, because now the air has a different temperature. So basically what it is, if you increase the temperature, you increase the speed of sound. I'm gonna call it SOS for speed of sound. So if you increase the temperature, you increase the sound. If the temperature increases by 1 degree, so 1 degree increase, a 1 degree increase is equal to a 0.6 meter per square increase in the speed of sound. So if there is a temperature increase of 10 degrees, then the speed of sound is going to increase to what? Well, it's going to increase by 6 meters per second. And then also same vice versa. If you lower the temperature, then that would lower the speed of sound by this same ratio. So if we decrease it by 1 degree Celsius, you decrease the speed by 0.6 meters per second. Okay, so now, since we're still talking about sound traveling through mediums and whatnot, let's now talk about reflection and just reflection, not refraction. I think refraction is next week or the next lesson. But reflection, we all know, is basically like, something bouncing off of something, right? You look in the mirror, you see your reflection. That's basically just light bouncing off the mirror and hitting your eyes. So let me first tell you how we draw sound and sound waves. Well, obviously, if you have a speaker, well, maybe you don't know, but you can kind of envision it. If you have a speaker just sitting there and you turn it on, the sound is going to emit in all directions, right? Well, we can draw that this way. Boom. So this is how we draw the sound waves. And we draw the direction of the sound as basically lines perpendicular to the waves. So the sound is basically going in this direction. Right? The sound's not actually traveling in a circle like this. It's not doing this. The sound's not going around like that, right? The sound is going outwards. So the sound travels perpendicular to these waves here that we drew coming outwards. So that's kind of just how we draw it. I think I might have skipped that part. But now imagine we have the speaker here and we have a wall right here. Boom. Speaker here, now you have a wall right there. So the sound's gonna just hit that wall, right? Boom, boom. Now, if you've ever experienced an echo, I'll say, then you know that sound can basically bounce off of objects and return back to you. That's basically what an echo is. So an echo is basically sound reflecting off of surface. Alright, so basically the sound from this speaker here is going to bounce off of this surface and then begin to go the other way. So looks something like that. So the sound comes out of the speaker here, hits the wall, and it's gonna bounce back the other way. And so I think there's a question in the mastering physics homework that I kind of just want to run through here real quick because it's a little bit math based. I think it goes something like, there is a bat and bats are blind, right? So there's a bat. We know bats are blind. And so bats basically see using echolocation. So they basically use echoes to, know where they're at in space and time. So I think it goes something like, there's a bat here, and he hears his echo after a certain amount of time. I think the bat hears his echo after maybe 0.11 seconds or something. So the question then asks, if this bat hears his echo in 0.11 seconds, how far away is it from, I think it's next to like a mountain or something. Just draw a wall. Right. So let me just see if I can find the question so I'm not messing it up. Okay, so it's actually a bat inside of a cave. Okay, so the bat's inside of a cave, so it's surrounded by walls. And then the bat emits some sound. So some sound comes out of the bat because it uses echolocation, right? So he emits some sound, draw it this way. The sound's gonna hit this wall and basically come back to the bat. And then based on how long it takes for the sound that he made to go to the wall and come back to him, he can figure out what his distance is to the wall. That's his distance. Boom. His distance, I'll call it distance D. So the question is, what is this distance if his echo comes back in 1.11 seconds, 0.11 seconds. So first you have to think, well, the sound is traveling at some speed, right? So since sound is traveling at some speed, we know speed or velocity basically is just the distance divided by the time. Right, so distance divided by time. equals the velocity. So we know we're trying to find some distance d, we have some time t, and we know the sound travels at some velocity. Okay, so we can kind of get somewhere with this. So we're looking for d. The distance traveled is going to be equal to the velocity times the time. Well, again, since this bat is basically in air, the sound that he emits is just going to be the speed of sound, right? Which is 340, roughly about 340. That's an estimate, roughly about 340. So now we know the speed, we know the time, so now we just want to know this distance. Okay, cool. So basically the sound travels two distances, right? So the sound travels from here to here. So that's like 1D going in that direction. And that's what we're trying to find, right? But with the way that echo works, the sound travels from here to here. So first it comes from the bat, right? Goes this way, some distance D. Then it bounces off of the wall and goes back to the bat. So for it to do this whole path, it takes 0.11 seconds. So that's basically a distance of 2D. So for an echo, the distance was actually 2D. All right, hope that makes sense. Because since it's an echo, we know the time it takes for the sound to go from the bat to the wall and then back to the bat. So the distance traveled, this distance D, is actually 2D. Because you could think going this way is 1D, and then it went from here back here, which is another D. So that's why this is a distance of 2D. So this should have been 2D. So now we're trying to solve just the distance from here to here, not the distance from there to there, and then back from here to here. So we just divide by 2. So distance is going to be v over t divided by 2. Boom. And then that should get you kind of what you want. You put the numbers in yourself. So hope that makes sense. I know sometimes there's like random math problems thrown in the Mastering Physics, but hopefully, this one will make a little bit more sense to you this time around. Okay. So let's see, back to the slides. So that's reflection, right? So now we talked about reflection. I guess now we can actually get into refraction. We talked about reflection. Now let's talk about refraction. Well, refraction is what happens when basically a wave, or here we could talk about sound. When sound basically changes medium, it's going to refract. And so let's list out some waves, actually. Some waves. We know sound is a wave, right? Light is a wave. Well, let's focus on these two, because these are two like just good examples to use. So let's use light. I think light is a little bit easier to understand when it comes to refraction. So if this is, let's call this water. Boom. So this is water, right? And we have sunlight. So sunlight coming in. So let's say like the sun's over here. Sunlight's coming in at some angle like that. Boom. So what refraction is basically when the wave, whatever the wave is that's traveling, goes to a different medium, the different medium here being water. So up here is air. Once it goes into this different medium, it's gonna bend a certain direction. It's gonna bend, now it's gonna go down this way. This bending of the light or bending of the wave is what we mean by refraction. So refraction is bending of a wave. Is, let's say, when a wave bends because it went into a new medium. Where up here, the medium is air, right? But then once the light gets in the water, the medium is water. And so light's gonna come down, it goes through the water, it's gonna bend. Okay, so this dotted line that I drew here is what we call the normal line. And this part of the wave over here called the incident wave, and this is the basically that outgoing wave. So this wave is the incident wave, this is the outgoing wave. Okay, so I think that's kind of a good idea of refraction right there. So now let's go back to sound waves, because sound waves can also refract if they travel in a new medium. Mainly if the medium is air and the air has like a temperature difference, right? So let's draw two scenarios here. Cut this in half. So over here we have warm air on the bottom. Up here we have cool air. Let's say over here it's the opposite. It's warm air, cool air. Boom. So you're standing here, you're standing right here, and there's a person, you know, a little kid over here that you're trying to talk to. And y'all are kind of far apart, pretty far apart. And so here, you know, you're yelling, you're trying to talk to the kid, but this kid can't hear you that well. And he can't hear you that well because as you speak, the air is going to be refracted, or it's going to bend upwards. So if I were to draw kind of how your sound wave is going to travel here. Not really good at drawing this. So here, basically, the sound of your voice bends upwards. Boom, like that. And that's if you have like warm air down here and cooler air up here. Your voice is gonna bend upwards. So it's gonna be difficult for that kid to hear you. Because notice basically the sound of your voice is being bent upwards. Whereas for the cool air situation, where it's cool air on the bottom and hot air on top, then your voice travels more so like this. It's gonna bend downwards. So here, this kid would actually be able to hear you a lot better than here if the kid was able to hear you or not. So in the homework, there's a professor who explains this pretty well. So watch that. He'll probably explain it a lot better than I did. But just know that basically sound is refracted in air as well because of temperature differences. Okay. So now let's talk about forced vibration and natural frequency. So I think these two concepts kind of describe themselves pretty well. Nothing really tricky here. Okay, so force vibration would be something like if I were to force something to vibrate. So if if there's a whole, bunch of people in a marching band and they're all basically, walking at the same rhythm, that would be a forced vibration because they're causing vibrations in the ground, causing the ground to like shake and vibrate, right? So that would be more so of a forced vibration. And natural frequency is basically how do you say? Natural frequency is kind of it's your own personal set frequency of whatever object. So like this marker has a natural frequency. This marker has a natural frequency. This eraser has some natural frequency. So basically what the natural frequency does is if you vibrate something at the natural frequency, it's going to cause resonance. An example of this is the opera lady who has a really, really nice voice. Opera lady, really, really nice voice. And she sings and she causes this wine glass to break, right? Well, what's causing it to break is the fact that she's shaking the molecules inside of this glass at the natural frequency. So if you were to shake it with a forced vibration, it may not actually break. But for a natural frequency, if you know the natural frequency, she may not know it like the number, but she can sing the natural frequency. And basically this natural frequency is hitting this glass here, causing it to vibrate just right, and then it's going to basically shatter and break. So I think in order to like explain this, it'd be a good idea to know about constructive interference and destructive interference. So actually, let me just erase this and talk about what interference is real fast. Interference. I spelled that wrong. Interference. That's what it's supposed to say. Try that again. Interference. There we go. So interference is kind of like what the word says. It's when two waves interfere with each other. So it's like if we have two speakers playing two different songs, the sound waves coming out of both of those speakers are going to interfere with each other, right? So it basically looks like something like this, and then we have another one over here. So these two sound waves are basically interfering with each other. So see how they overlap here, how they overlap there. So they're interfering with each other. And so waves interfere in one of two ways. They can either interfere constructively or destructively. So when waves interfere constructively, they basically add amplitude, or they increase amplitude. Increase amplitude. I'm just amp for short. And for destructive interference, then basically the amplitude is reduced. So let's see, reduced amplitude. And so you can kind of think of this as, in everyday language, people may say like, oh, I like your vibes, or I like your vibrations, or, me and you are on the same wavelength, right? So if two objects have the same wavelength, so let's say some two waves like this, if two objects have the same wavelength, when they interfere with each other, they interfere constructively. So meaning that when these two objects interfere, we get a new wave that's way bigger. See how the amplitudes, these two amplitudes here, boom, those two amplitudes basically add up to make this big amplitude because they interfere constructively. And so kind of easy to remember that because people kind of already use it in regular language. Oh, like, me and you are on the same wavelength. So basically, those two people interfering with each other must be interfering constructively because they both kind of amplify each other. Or, have the same kind of language going vice versa. People say, I don't vibe with you, or we're not on the same wavelength, or not on the same page, or something like that. So if we have two opposite waves, so one going like this, and then one going like this. So notice these are like the same wave, but this one starts by going up, this one starts by going down, then up. So these two waves, since they're opposite, are gonna interfere destructively. So basically they're gonna cancel each other out. You're just left with a straight line. So that's how waves interfere with each other or interact with each other. If there's more than one wave, they can interfere either constructively or destructively. So kind of going back to that natural frequency thing. It's supposed to be natural frequency. So now, basically, natural frequency is basically the natural frequency of an object, right? So now, resonance is when two waves interfere with each other constructively. So resonance is kind of a form of constructive interference. Yeah, close enough. So constructive interference. So then, back to the person singing. Then we got this wine glass over here. This wine glass has some natural frequency, or you could say a natural wavelength, right? Because it has little molecules inside of it. Those molecules are vibrating by some amount, and so they must have some wavelength associated with their vibration. So when this wave interferes with the basically waves inside of this wine glass, resonance happens when they basically interact constructively. So you could kind of imagine with this wave plus this wave interact with each other constructively, the amplitude is going to be doubled, and then that increase in amplitude is what causes this glass to break. because so much energy is being given to this glass of wine, or wine glass. So yeah, so since both light and sound are both forms of waves, so sound and light are both waves. So light can interfere or light can interfere with other light, sound can interfere with other sound. Sound can reflect and refract, just like light can reflect and refract because they're both waves. So basically, the language of waves applies to both sound and light. Okay, so now let's talk about beats. Beats. So a beat is basically kind of I would describe it as a pulsation that you hear, from a sound. Usually it's periodic, right? Something like that. But a beat happens when there's two sounds basically interacting with each other, and they cause some kind of pattern, some type of beat. So if I have two, they call these tuning forks. And basically what tuning forks are they're just kind of like weird looking forks, and if you hit them, they vibrate by a certain amount, causing certain sound waves. So let's say this one has a frequency of, let's just say 50 hertz. This one has a frequency of, let's say 55 hertz. Right? So if we play both of these tuning forks, and this one has frequency of 50, this one has a frequency of 55. If we play both of these tuning forks, they're going to interfere with each other and make some type of beat. So the beat is going to be basically the difference between the frequency. So here the beat given is going to be, it's going to make a beat of 5. I think it's measured in hertz. I think beat's measured in hertz. Let me check. Yeah, so beat is also measured in hertz. So if we play these two tuning forks, then it's going to make a beat of 5 hertz. If I were to add a third one, a third tuning fork, and it has a frequency of, let's say 53, then what beats with these three tuning forks then produce? Well, if we look at these two are going to produce a beat of 3 hertz, right? Because those two waves are going to interfere with each other. And then these two are going to produce a beat of, 2 hertz? Because we did 55 minus 53 to get 2. Here we do 53 minus 50 to get 3. And then also the 50 and a 55 are also still going to interact with each other. So it's also going to make a beat of 5 hertz. Boom. So now these are the beats that are produced by these frequencies. So that's pretty, well, that's kind of all you need to know for, beats and how they're produced. So now back to the slides. So we talked about interference, we talked about reflection, refraction, beats. So now let me go over the Doppler effect. So I'm gonna go over the Doppler effect, and then I'm gonna go over shock waves, and then that'll be it for this lecture. So now let's go over the Doppler effect. So in words, the Doppler effect is basically what happens when it's basically the change in frequency due to motion. Simple words. The Doppler effect is just the change in frequency due to motion. So if you have sound in motion, then there's going to be some Doppler effect. An easy example of this is, let's say you're standing outside and there is an ambulance, coming from down the street. So you're just standing there. You hear the ambulance as it gets closer and closer, right? But as it gets closer and closer, the sounds that it make seem to sound like they're at a higher pitch, right? It's kind of it doesn't just get louder, but the pitch of it kind of changes. So basically what's happening is you're standing here, then we have the ambulance over here, and it's driving in this direction. So as it drives in this direction, it's giving off some type of sound waves, and then you hear those sound waves, but the sound isn't just coming at you, the truck is also coming at you. And so that changes the frequency that you hear. So I guess to get a little deeper into this, let me go over the bug in the water. So if we have like some bug here, I don't know, some bug, it's like standing on top of the water, like bugs do. It's standing on top of the water, and let's say it's like bouncing up and down. So it's causing waves to go outwards in the water, right? But it's just standing there going up and down, so it's making these waves, kind of go outwards like that. But now, let's say the bug then starts to move, right, in the water. How is that going to affect the waves? So let's say now he's moving. So as he moves in this direction, the waves that it produces look more like this. Boom, right? So notice that like the waves are kind of skewed to the right, because as he moves this way, he's basically kind of moving the wave front, so we say, to the right. And so it's like getting shorter here because he's moving in this direction, but it's getting longer behind him because he's moving away from, behind him. So you can kind of imagine if you were over here versus whether you're right here. If you're back here, this is basically the frequency of the waves that you're going to feel. They're much more spread apart, right? So since they're spread apart, that basically means the waves are stretched out back here. And so you're going to hear a lower frequency. Whereas here, the waves are closer to each other, or more like faster, because the bug is moving in this direction. So here you're going to feel, more waves or a higher pitch or a higher frequency because you're on the right side. So all that to just kind of describe the Doppler effect. So now let's talk about a car. So now if we say we have a car, and its sound waves look like this. Right? They look like this because they're moving in this rightward direction. So you kind of think of this dot being the source is moving, and since the source is moving, that causes the sound waves outwards to look kind of skewed. So now you kind of imagine, let's say, got a person standing over here, and a person standing over here. This person is going to hear a higher pitch because he's being hit with a higher frequency of the waves. Notice how these are like a lot closer to each other. So this person is going to be hit with a higher frequency, whereas this person, notice the waves are a lot more spread apart. He's going to hear a lower frequency. And that basically is what the Doppler effect is. So, question number 48, just I guess to check your knowledge, says when a fire truck or when a fire engine approaches you, it says A, the speed of sound increases, B, the frequency of sound increases, C, the wavelength increases. Okay, so that's a good distinction to make. So the speed of the sound here, the speed of sound is still 340. That didn't change here. The only thing that did change is the frequency. So frequency changed. Speed stayed the same. So, or I should have said same speed, not some. Same speed. So the Doppler effect changes the frequency, but the speed of the sound is still the same. And so again, Doppler effect is basically an effect due to a wave. So Doppler effect can happen in light or in sound. It can happen for light or sound. So now let me talk about shock waves and sonic booms, and that'll be it. Because I know this is getting a little long. Okay, so the last thing, shock wave or a sonic boom. So if you've never experienced a sonic boom, it's a kind of an eerie feeling. So let's go back to the, basically a shock wave happens when there's an airplane. Airplane goes so fast, right, that it moves faster than the speed of sound. Once it starts to move faster than the speed of sound, it basically, let's say break the sound barrier. I'm gonna show you what they mean by that. And it causes a shock wave or a sonic boom. So let me draw a few scenarios. Okay. Okay. All right. So here, you can imagine like this is the object inside the inner circle. Here it is here, and here it is out here. This blue dot would be like the airplane, all right? So this airplane here it's moving, pretty fast in air. It's just picking up some speed. Here, it's moving even faster. It's moving even faster. You can tell because, kind of the tail of the wave front, or these circles here are the wave fronts. It's kind of getting stretched out even more. So here it's going even faster. Now here, you can see basically the plane is starting to break out of this sound barrier. So it's starting to break out of this circle of sound that surrounds it. And once it breaks out of that, it causes, so it goes a little faster. It basically outruns the speed of sound, so to say. So you can imagine if you're on the ground down here. So there's 3 people on the ground. Plane up here, and it's going really, really fast. Breaking the sound barrier, right? And so yeah. So this is basically, this arrow or this line here is the direction of which the sound is heard. So you can kind of imagine this person here, these people are kind of far apart. This person here, he can see the plane, so he sees it, and he doesn't just see it, but the plane actually passes him overhead. So the plane passes him, but he still doesn't even hear it, or he doesn't hear the sonic boom. Once the plane has already passed him, then the sonic boom will hit him a few moments later. So it's odd because usually you can, with your eyes, see the cause of a sound, and then that sound basically hits you kind of at the same time, right? But here, you see the plane first, and you don't just see it, but the plane actually flies overhead, and you don't even hear it at all because the plane is moving faster than the sound can reach you. So imagine if a person is standing across the room from you and they tell you hi, but then right after they say the word hi, they run to you and touch you before before the sound even hits you. That's kind of an extreme example to think about, but that's basically what's happening here. You're basically seeing the airplane fly ahead first, and then the sonic boom hits you a moment later because the plane's moving so fast. Okay, so now the rest of this, it just talks about standing waves and harmonics. I think all that is pretty straightforward, but I'll go over it real quick here. So if you have a wave, a standing wave is basically when, if you have like a jump rope and you whip it up and down, it kind of makes like this pattern that looks like this. Or I guess a jump rope really is just this, right? Boom. So this would be like for a jump rope. So this is what we call a standing wave because it kind of just stands there. And we call this the first harmonic. Right? And so you can kind of imagine there's a second harmonic that looks like this. So that's the wave, and then it kind of stops here and it comes back. This would be the second harmonic. And then there's a third one. Just messed up. third harmonic, and so on and so on. You basically keep on making these. And so these two outside points are called nodes. So basically call each point where they kind of overlap a node. So that's a node, that's a node, this is a node. And let's see what else, I think that's about it. As far as harmonics and nodes. So that's it for this lecture. I know some of this is a little tricky. Let me just give you the equations that you really need to keep up with. So the velocity is what? Frequency times the wavelength. Frequency is 1 over the period. And the speed of sound is 340. Well, it's exactly like 344, but sometimes we round it. So these are kind of like the 3 main equations that you need for this chapter, and just kind of understand how to label a wave on a chart, right? So knowing that from here to here is the wavelength, knowing that from here to here, up and down, is the amplitude, and the amplitude is associated with how loud it is, and the frequency is associated with the pitch. So it is associated with the pitch. Yeah. So good luck. See you for the next one.